Today, we're presented with an array representing student heights. Our challenge: determine how many students are not standing in their correct, non-decreasing order. It seems straightforward, but there's a trick to doing it optimally. Given an array of integers called heights, where height sub I is the height of the ith student, we need to find the number of indices where height sub I does not equal the expected height sub I if the students were arranged in non-decreasing order. Essentially, count the mismatches between the current array and its sorted version. The most intuitive approach is to first create a copy of the original heights array. Then, sort this copied array to get our expected order. Finally, iterate through both the original and the sorted arrays simultaneously, comparing elements at each index. If an element in the original array doesn't match the corresponding element in the sorted array, we increment a counter. This approach works, but sorting takes n log n time due to comparison-based sorts, and the copy uses linear space. The key insight for optimization comes from the height constraints. Heights are between 1 and 100. This allows us to use a counting-based approach. We declare a frequency array, let's call it counts, of size 101. We iterate through the original heights array once, populating counts by incrementing the frequency for each height encountered. Now, counts tells us exactly how many students there are for each height, effectively representing our sorted order without actually sorting. We then iterate through the original heights array again. Simultaneously, we maintain a pointer for our expected height, starting from 1. For each position in the original array, we find the smallest expected height that still has a count greater than 0. If the current student's height doesn't match this expected height, we increment our mismatch counter. After a match or mismatch, we decrement the count for that expected height, moving to the next student or the next unique height if the current one runs out. Let's trace this with heights 1, 1, 4, 2, 1, 3. First, we build our counts array. We'll have 3 1s, 1 2, 1 3, and 1 4. All other counts are 0. Now we iterate through the original heights. At index 0, height is 1. Our expected height starts at 1. Count sub 1 is 3, so we expect a 1. Current height is 1, which matches. We decrement count sub 1. At index 1, height is 1. Expected is still 1. Count sub 1 is 2. Match decrement count sub 1. At index 2, height is 4. Expected is 1. Count sub 1 is 1. Current height 4 does not match 1. Mismatch. Increment mismatches. We decrement count sub 1. At index 3, height is 2. Expected is now 1, but count sub 1 is 0. So we advance expected to 2. Count sub 2 is 1. Current height 2 matches expected 2. Decrement count sub 2. At index 4, height is 1. Expected is now 2. Count sub 2 is 0, so we advance expected to 3. Count sub 3 is 1. Current height 1 does not match 3. Mismatch. Increment mismatches. Decrement count sub 3. Finally, at index 5, height is 3. Expected is now 3. Count sub 3 is 0, so we advance expected to 4. Count sub 4 is 1. Current height 3 does not match 4. Mismatch. Increment mismatches. Decrement count sub 4. After iterating through all students, our mismatch count is 3. This is correct because 3 students were not in their sorted positions: the 4, the 1, and the 3. You'll spot this pattern when you need to sort or compare an array to its sorted version, but the elements have a very small, fixed range. This constraint is your signal that a counting sort or frequency array approach can offer significant speedups over general-purpose sorting algorithms. Time complexity is O of n, as we iterate through the array a constant number of times. Space complexity is O of 1, as the counting array size is fixed and small, independent of n. Mastering these constraint-based optimizations is key. Try the next problem applying this counting pattern. If you found this helpful, please like and subscribe.